Hello again. My name is Meg. I am a research scientist at Georgia Tech, and today I'm going to be giving an introduction to CBC Science. Of course, uh, the first thing is to define what CBCs are. CBCs are compact binary coalescences, and compact objects means these are things that have a very high mass to radius ratio, so very dense objects. And the more compact an object is, the more extreme the curvature of spacetime around that object will be. In LIGO, Virgo, and Cagra, the compact objects that we are concerned with are neutron stars and black holes. Neutron stars are the second densest known objects in our universe. They typically have masses between maybe 1.2 and 2.5 times the mass of our sun. That exact range is still unknown, but their radii are only about 10 kilometers, so the size of a relatively small city, or in this little animation or little plot here, not much bigger than the city of San Francisco. And this is a great website where you can figure out what a neutron star would look like right above you. But these things are very dense. They are formed in supernovae when the core of a massive star collapses, and the density is so great that the protons and electrons are squeezed together into neutrons, hence why they are called neutron stars. Past neutron stars, the densest known objects in our universe are black holes. These are objects that are so dense that even light cannot escape from the extreme spacetime curvature around a black hole. And this means that we can't directly observe these things with electromagnetic radiation, but astronomers can infer the presence and some properties of black holes based on how things move around them. Black holes cover many, many, many orders of magnitude, from a couple times the mass of our own sun to billions of solar masses. And these much larger black holes, these are supermassive black holes. These are what we typically find in the center of galaxies. And of course, they're very interesting, but what we're concerned with now is the lower end of this mass range, so up to about 100 times the mass of our sun. We call these stellar mass black holes because, like neutron stars, they are mostly formed by the collapse of massive stars. However, these objects are more dense, so that supernova remnant is so massive that even the neutron degeneracy pressure can't balance the gravitational pull, and they collapse further into this black hole. So now that we talked about what the compact objects are, what is a binary coalescence? Hopefully the binary part is clear enough. It means there are two objects. And the coalescence means that they are spiraling in towards each other with a shrinking orbit, ultimately merging into a single object. And because the orbit of these two objects is shrinking, energy must be carried away, and that is in the form of gravitational waves. So as these objects accelerate, rather than just causing a stationary dent in space-time, they're causing ripples or waves. And the more compact an object is, the bigger those ripples will be, which is why compact binaries are the most promising and abundant source for our detectors. So for us sitting here at the detector or at our computers looking at detector data, what does a gravitational wave look like? So I think you heard yesterday that our detectors measure strain, which is the fractional length change or how much the arms are stretching and squeezing. A gravitational wave signal from a CBC during the in-spiral phase, which is the last orbits of that merger, the frequency and amplitude will sweep up. And then during the merger phase, which is when the horizons or the edges of the two compact objects touch, this is the merger phase. This is when the amplitude of the gravitational wave is the biggest or the greatest. And then you have the ring down phase where that remnant object settles into a steady state. And this characteristic sweeping up in frequency, you might hear people call a chirp. You can convert it into the audio band, and it does sound like a chirp. The details of a given waveform, like how fast it sweeps up in frequency, how big the amplitude is, when it merges, or at what frequency it merges, gives us information about that binary system from which the signal originated. So from the waveform, we can infer physical properties like how big the component masses are, how fast they're spinning and in what direction. If it's a neutron star, you can learn about the tidal deformability or how much it stretches and squeezes. And then you can also learn things about the location and orientation of the signal source. So, whether the orbital plane is face on or edge on, as well as where it is in the sky. And Daniel's talk tomorrow will go into more detail on how we measure these things or do what we call parameter estimation. So the very first gravitational wave signal was observed in September of 2015. At this point, it was only the LIGO detectors observing, and we inferred that the signal was from a compact binary coalescence, specifically originating from a black hole binary system with component masses each around 30 solar masses. And so you can see here, we have that nice characteristic chirp that we saw, and these are the inferred waveforms, both based on our models and a sort of more flexible waveform. And it looks exactly like what we expected from CBC. And this first detection, of course, was unbelievably exciting. It, confirmed some more of Einstein's theories, ultimately led to a Nobel Prize for Ray Weiss, Kip Thorne, and Barry Barish. All around, just incredible. But we're approaching the 10th anniversary of this detection. And in that time, things have changed quite a lot. A single detection now is usually not that exciting. We're getting them when the detectors are on almost every day. And this figure shows the total number of CBC detections over the observing time. So we have had 4 observing runs, or we're within the 4th observing run. And you can see how the number of detections has just grown like crazy. Most of that is due to improved detector upgrades. But as of the end of 03, there are 93 confident detections. These have all been published in our gravitational wave transient catalogs. And in 04, we haven't published the transient catalogs yet. That analysis is ongoing, working very hard. But we have been releasing public alerts of when we get potential candidates. So that's what this lighter line through 04 is. And so, the exact numbers here will change a little bit, but we're around 300 candidates now, which is very exciting, very different from 10 years ago. In Prathmesh's talk next, we'll go over like how we find these things and probably what some of these public alerts are. But for now, I'm going to talk about what we do with the CBC detections. So the first most basic thing is just discovering what's out there. So this plot shows the masses of all the CBCs that LIGO, Virgo, and Cagra have detected so far. The black holes are in blue and the neutron stars are in orange, and so each shows the 2 component masses and the mass of the final remnant after they merge. This plot also shows black holes and neutron stars that have been observed with electromagnetic astronomy, so black holes in pink and neutron stars in green or yellow. I think that's yellow. We can see that we're really starting to fill out our understanding of what's out there. Like above about 20 solar masses, we really hadn't observed any black holes yet. So we're probing a region that was not accessible before with electromagnetic observations alone. And so by combining these detections and these measured masses, as well as some other parameters, we can try to find a population model that describes, in this case, the distribution of masses of distribution of the black holes in these binaries. One population model that seems to fit the data well is this power law model plus a Gaussian peak. This is the inferred distribution based off of the most up-to-date gravitational wave transient catalogs. And some interesting things we can learn from this distribution is about the maximum and minimum masses we see in these CBC systems. So looking first at this high mass region, there exists this theoretical mass gap somewhere above 50 solar masses. Where that mass gap starts is still unknown and definitely an interesting question that people are trying to answer. And stellar evolution models predict that very massive stars won't form black holes. Instead, they'll blow apart and lose all their matter, so they can't collapse into something very compact. So we don't expect to see black holes formed from stellar collapse in this region. And indeed, our population doesn't support many black holes out here. However, there are some in binaries that we've seen. Notably, this one event that we called GW 190521. If I didn't say before or didn't hear yesterday, gravitational waves are named by the day we find them. So this was on May 21st, 2019. And this was a very massive black hole binary. And specifically, one of the masses, the primary mass, is somewhere between 60 and 100 solar masses. This here shows our probability distribution of what we think each black hole mass is based on the signal we got. And we define M1 to always be the more massive one, which is why it has this odd cutoff here. But again, so, we think the heavier mass is maybe around 80 solar masses, which pretty definitely falls in most of the theoretical models of the mass gap. So where did this black hole come from? Well, one possible interesting explanation is that it is a second generation black hole and that it itself was formed by a merger of two previous black holes. Oops. Okay. On the lower end of the distribution, in this case, we have an observational mass gap, where E&M observations haven't really seen anything, and in particular, black holes between about 3 and 5 solar masses. So we don't really know what the minimum black hole mass we expect to see is, specifically black hole masses formed by stellar collapse in binaries. However, most population models show a fairly sharp cutoff around 5 solar masses. However, there are, again, some interesting outliers that might not fit with some of the models. So one in particular is this GW 1908-14. And in this system, the lighter mass is somewhere around 2.5 or 2.6 solar masses, which would either be an extremely heavy neutron star, but more likely is a very light black hole. And this event alone can have a big impact on the estimated minimum mass of black holes in binaries. So it's quite interesting to figure out how the system could have been formed, or investigate whether it is actually drawn from a different population than most of our other compact binaries. Along with the masses, we can use the measured spins and spin orientations to learn about how these compact binaries form into binaries. Two different formation scenarios are isolated and dynamical evolution. In isolated evolution, you have two stars that are in a binary, orbiting each other. They each go supernova at some point, not at the same time, and they end up as two black holes in a binary. For dynamical formation, the black holes are formed in separate systems, and they're in a dense enough environment that they end up in binaries via some dynamical capture. For the isolated channel, we expect for the spins of the black holes to generally be aligned with the angular momentum of the orbit and with each other. Whereas for dynamical, we expect the spins to be more sort of isotropically distributed in direction. So far, the binaries observed by LIGO, Virgo, and Cagra seem to have spins that are aligned, so basically the same angle there, indicating that the isolated evolution is probably the primary, probably not only formation channel. So I've mostly been talking about black holes so far, but let's talk about the science we can do with neutron stars and compact binaries. We don't have as many of these observations, but at least one we have can tell us a lot. And one big question is, how exactly does matter behave at extreme densities? So neutron stars are way denser than anything we can make in a lab on Earth. So they can teach us stuff about nuclear physics that we can't, learn in our own experiments. Specifically, we're interested in this thing called the equation of state, which can be used to relate microscopic properties of nuclei to observable properties of neutron stars. When neutron star When neutron stars merge, one of the properties that we can measure or constrain is this thing called the tidal deformability, which is basically a way of quantifying how much a neutron star can stretch into some non-spherical shape within the gravitational field of its companion. The LVK so far has seen two binary neutron star mergers, with one of them, GW 170817, being very, very loud. And with that event, we see support for smaller tidal deformabilities, or tidal deformabilities are denoted by this parameter lambda. This means there's more evidence for softer equations of state or more compact neutron stars. So it prefers smaller radii for a given neutron star mass. Another exciting thing about binary neutron stars, binary neutron star mergers, is that we can observe the same system with gravitational waves and across the electromagnetic spectrum. So this event, GW 170817, this was, after 15914, probably the most exciting, biggest event within LIGO Virgo CAGRA. So almost instantaneously after the gravitational wave signal hit the detectors, two satellites, Fermi and Integral, detected a gamma ray burst. The gamma ray burst was cool enough on its own because CBCs, had long thought to be a source of short GRBs, but this was the first confirmation, or at least very strong evidence. But then even after that, using the estimated sky location from LIGO and Virgo, astronomers were able to pinpoint the exact place this signal was coming from and observe this signal across all different wavelengths. And almost every telescope in the world, I think, was pointing at this event at one point. So this thing that the telescope saw was called a kilonova, and this kilonova was observed over many months. And that spectrum and the evolution of that spectrum helped us understand how many and which heavy elements were produced in this neutron star merger. In particular, a lot of the precious metals, so platinum and gold, come from kilonova rather than supernova for the most part. This multi-messenger observation also allowed us to make a measurement of the Hubble constant. So you're probably familiar with the Hubble constant. It is a measure of how fast the universe is expanding. And using the joint observations of 170817, you can get an independent measurement of the distance from gravitational waves and the redshift from the E&M identification of the host galaxy. And then from that, you can get an estimate of the Hubble constant. This is useful because you may have also heard that there's currently a Hubble tension, so different methods of estimating the Hubble constant are not agreeing with each other, so it's nice to have another method to try to resolve that tension. Currently, the precision isn't enough to totally resolve the tension, although luckily it's consistent with both other H0 measurements, but with more detections, we can maybe narrow down that estimate. And then we also have tests of general relativity. So is our understanding of general relativity correct? Does it describe the universe? One of the most powerful aspects of directly observing gravitational waves is that it allows us to test GR in these strong field dynamical regimes. So I'll run through just some, not all of the tests of GR that can be done with compact binary coalescences observed by LIGO, Virgo, and CAGRA. So the first is known as the residuals test. And here we subtract our best fit waveform generated by general relativity-based models from the detector data. What's left over should just be noise, uncorrelated between the detectors, stationary, and consistent with what we expect from our detectors. If there's any leftover signal, especially leftover signal that's coherent across the detectors, it could point to missing physics, such as an incomplete model of general relativity. So far, all of the events we've seen so far do not leave any residual power, so our models seem sufficient. The second test checks the consistency between different phases of the signal. So we split the waveform into the in-spiral and post-in-spiral phase, and we run separate parameter estimation on each segment independently to infer the final mass and spin of the black hole. We then test if these results are compatible with each other. And again, so far our models seem good, seem consistent with GR. The estimated difference between these final masses and spins is right around 0. And finally, another prediction of GR is that gravitational waves, like electromagnetic waves, travel at the speed of light. The best test of this came again from the binary neutron star merger GW 170817, which had an associated gamma ray burst 1.7 seconds after merger. And given that this event is so far away, 100 something million light years away, this means the speed of light and the speed of gravity don't differ by more than 1 part in 10 to the 15, which is a very tight constraint. So everything we've seen so far does not deviate from GR, but with future detectors where we get much louder signals, we can provide even more stringent tests on the validity of GR. So I am going to give a little bonus too about beyond CBC Science, because a lot of my work so far has been in beyond CBC things, and I think it's interesting. So we can kind of think, people sometimes discuss LIGO, Virgo, Cagra searches and sources on 2 axes, one being the duration, so short duration transient events or long duration, and how well modeled the signals, or sometimes how well modeled the search is. Compact binary coalescences are, we tend to think of them as short duration. They're transient events. They, they last milliseconds to maybe up to a minute in our detector, and they're very well modeled. We have good GR-based waveforms for these, as I talked about earlier. On the other hand, we have short but relatively unmodeled sources that we could potentially, I didn't say already, the only thing we've seen so far is compact binary coalescences, but we could potentially get other things. So other sort of short duration signals that we could get, and some things we can learn about them. First, we have core collapse supernovae, so those things that form black holes and neutron stars, we could detect gravitational waves from them. From that, we could learn about the supernova explosion mechanism. There's maybe these things called cosmic strings, which are topological defects in the universe. And of course, something completely unknown. This is a new way of looking at the universe. It would be great to find something new and surprising. On the other end of the spectrum, we have these things called continuous gravitational waves, which are very long lasting, so years more at a time. And they're well modeled because they're basically quasi-monochromatic. And we expect these to come from mountains on neutron stars, where mountains is kind of a misnomer because they're, maybe millimeters of deformation. But if we do detect one of these signals, it could again help us learn about extreme matter, put some constraints on what's going on inside of neutron stars. And then finally, there's the stochastic gravitational wave background. It would be from many overlapping indistinguishable signals. And this could come from like many CBC sources where we can't individually distinguish them. But again, that could help us learn about the overall population and sort of the rates of mergers. And that is all I have today. So just as a summary, we've gotten over 90 CBC detections through the first 3 observing runs. This has enabled new science that we couldn't do with E&M observations alone, such as, how stars die and form binaries, how matter behaves at some of the most extreme densities, if GR is the correct model of gravity, and O4 is ongoing. We should have some results reported this year, so you can look forward to a lot more CBCs, a lot more science, and maybe one day some non-CBCs as well. Thank you.